In previous videos, our focus was on constructing confidence intervals for the population proportion. In this video, our goal is to learn how to construct a confidence interval for the population mean, represented as mu. Now, this can be based on either a small sample or a large sample. If it's a small sample, please note we must require that that small sample is drawn from a normal population for us to be able to use a T interval. However, if the confidence interval is for a population mean based on information coming from a large sample, then we don't care about whether it is from a normal population or not. And that is many thanks to the central limit theorem. We can still use the T distribution. And if you are more of a graphic person or a visual person, well, earlier we went this route, which is to study how to find confidence intervals for population proportion. This time, we would like to look at how to find the confidence interval for population means. If the sample size is large, that is greater than or equal to 30, you're good to compute the T interval using this formula. Otherwise, if your sample size is not greater than 30, that is, it's a small sample, then for you to be able to compute the confidence, a T interval, you must require that the data come from a population that is approximately normal. If that condition is met, you are still good to use the T interval formula. However, if we cannot verify that the data could come from a population that is approximately normal, then we have to use non-parametric methods or bootstrap method. These would not be covered in this topic. So without any further ado, let's get to it. We just talked about the T interval. This is based on the T distribution, unlike the confidence interval for the population proportion that was based on the normal distribution provided certain conditions are met, namely P at times n times 1 minus P at is at least 10. The T distribution has a little bit of a history to it. You're welcome to read through the provided history, but I'm not going to read through that in this discourse. So you have values for every T distribution. It is always associated with a degree of freedom. Just remember that just as a normal distribution must always has its mean and a standard deviation for you to find any probability associated with any random variable having the normal distribution, then for the T distribution, it has what? A degree of freedom. The T distribution is very, very similar to the normal distribution, except that at the tails, it has heavier tails. There are more proportions in the tails as compared to the normal distribution. And then the main parameter or descriptive feature of the T distribution is what we call the degree of freedom. And what you would observe is that the T distribution is used when the standard deviation is estimated using the sample standard deviation. It has relatively more scores in the tails, and it approaches the standard normal as the degree of freedom increases. These are the basics you need to know about the T distribution before you use them. So let's see how it is used in practice. We would like to compute critical values based on the T distribution. This example requires us to determine the T value in each of the cases. Question A, we have to find the T value such that the area in the right tail, so right tail, this will be the right tail, is 0.02 with 28 degrees of freedom. The T distribution is approximately having the normal distribution, except that the tails are heavier. So where is the right tail? This is the right tail here. So we want the area in the right tail to be 0.02, the shaded area there. So let me do this. We want this size to be 0.02, and the degree of freedom, df, is 28. So we want to find that cutoff point. So to help us, we go to StatCrunch. So here we are in StatCrunch. I'm going to close the normal calculator, and I'll go to Start, go to Calculators, and go to the T calculator, T right here. Click on T distribution. I'm going to drag this over and then open this up. Well, in this question, what is my degree of freedom? 28. So I am going to supply 28 to StatCrunch, 28. And the next thing is, what is the size of the area? 0.02. Okay, so I will put that in the area for probabilities, 0.02. And the next thing I need to alter is, what tail am I looking at? Right tail. So that is greater than or equal to. I'll need to adjust that here. So choose greater than or equal to. And so it means the number 2.1539 cuts off the upper 2% of the tail of the T distribution with 28 degrees of freedom. So in this case, that is what I need. So this is my critical value, 2.1539. So that value, 2.1539, this is that critical value I need. Then the next question B, we have to find the T value such that the area left of the T value is 0.15 with 17 degrees of freedom. So again, I'll sketch the T distribution with heavier tails, and I want the area left of a particular unknown T value is 0.15. So that unknown value, this is the T value that is unknown, and the area to the left is 0.015, so 0.15, and the degree of freedom is 17. I can go to StatCrunch. So back in StatCrunch, the degree of freedom is 17. I want the area to be, according to the question, to be 0.15. So I need to adjust that to 0.15. And then I want it to be on the left tail. So this is to the left, right here. As you can see, the arrowhead. So this is negative 1.069. That is the T value I need. So I'm going to erase this. I have my final answer, negative 1.069. That is the T value we want to find. That is the answer. Then question C tells us to find the critical T value that corresponds to 50% confidence. And we're to assume degree of freedom to be equals to 26. If we want 50% confidence for an interval, that means we're looking at between, the area between. So this area between is 0.50, and I want the critical T value here. So I am going to set the degree of freedom to 26. And I'm going to choose an interface that accommodates a problem like this. So going back, I am going to change this to between. And again, don't forget the degree of freedom is 26. So I'll alter that to 26. And then in this case, I want 0.50, and I will compute. So that will be between negative 0.684 and positive 0.684. So those are the critical values, negative 0.684 and positive 0.684. So that completes that part of the question. Take note, we're going to need this when we're computing confidence intervals, and that is why we've spent time on it. So with that said, we proceed to the next example, and that has to do with checking the assumptions for constructing a T confidence interval for the population mean. And in this example, we are told that the data from a simple random sample with 25 observations, n equals 25, was used to construct the plots given below. So the normal probability plot that was constructed has a correlation coefficient of 0.945. The question before us is to judge whether a t-interval could be constructed using the data in the sample. Recall that this is a normal probability plot. This was discussed when we were learning about the normal distribution. So, what information can we garner or gather from this plot? We can tell from the plot that we do have some deviations from the straight line plot, and some of these points actually get out of the confidence band. So from the plot above, we can say that the normal probability plot does not suggest that the data could come from a normal population, because even the correlation coefficient of 0.945 is less than the critical value. How do we get the critical value for n equals 25? Here we go. We can go back here, and this is a sample question, and you observe that there is a table of critical values. For n equals 25, this is equal to 0.959. So, taking that back, I can tell that the correlation coefficient of 0.945 is lesser than 0.959. Lesser than 0.959. When that happens, it is a numerical testament to the fact that this data could not have come from a normal distribution. And if you plot a box plot, you will find out that the box plot of the data also shows outliers. So a t-interval could not be constructed in this case. This is an instance that ties with what we were saying when we started, when we said that when the data does not come from a normal distribution and the sample size is lesser than 30, we will have to use non-parametric methods or bootstrap. This is just a case to help us note when we would have to go more than the methods learned in this class. So with that said, we continue to the next example. But before we do, let's note a couple of things. You should note here that there are two problems why a t-interval could not be constructed. One, the sample size was lesser than 30. Two, the sample data evidence could not show that the data could come from a normal distribution, which we saw using the normal probability plot. With that said, let's proceed to the next example. In this example, we're told that a simple random sample of size n is drawn. The sample mean x bar is found to be 18.8, and the sample standard deviation s is found to be 4.2. A. Construct a 95% confidence interval for the population mean if the sample size n is 34. In order to answer this question, a couple of things are worthy of note. You have the sample mean, which is x bar. So please note this for further examples. Sample mean is always represented by x bar. It is 18.8. You have the sample standard deviation, and that is s, lowercase s, which is 4.2. Then we have the sample size in this part of this problem, which is n equals 34. And we want to use these three pieces of information to construct a 95% confidence interval for the population mean, which is represented by mu. This will be equal to, we need to find the lower and the upper bound. Just as we did in the case of the population proportion, we can use StatCrunch to compute this, make this computation. Please note that the sample size here is 34. This is greater than 30. So if we go back to our template here, when the sample size is greater than 30, we're good to just directly compute the confidence interval without requiring that the data should come from a population that is normally distributed. So based on that, we are good to go in this case. That is the 95% confidence interval for the population mean using StatCrunch would be done as follows. Go to Stats. This time, you're working with a T interval, so you want T statistics for one sample, and you want to go to with summary. So with summary, you want to key in the sample mean. The sample mean in this problem is 18.8. The sample standard deviation is 4.2, and the sample size is 34. So 18.8, 4.2, and 34. Let's key them into StatCrunch. So you have 18.8, and you have 4.2, and the sample size is 34. So remember, these values came from your workplace, from your workbench. So we want a 95% confidence interval. So we want to make sure that this is selected. Confidence interval for mu, 0.95, and compute. And you have the lower limit, which is 17.3345 and 20.26. So I am going to take this to 2 decimal places in this case. So I have 17.33 to 20.27. So here on your screen, I have what? Those values. This is the lower bound, 17.33 and 20.27. Question B. We have to construct a 95% confidence interval for the mean if the sample size is now 51. So let's see. We have the same parameters earlier, except that our n is now 51. So we're going to go back, go to, so here we are. I can go, since I'm still using very similar information, I can go to options here and edit. And I have 18.8, 4.2. The sample size is the only thing that is changing in this part of the problem from 34 to 51. So I can change that to 51 and compute yet again. This time I have 17.62 to 19.98. Let's write that down first. So when n is 51, we have 17.62 and 19.98. The last part of this problem says, how does increasing the sample size from 34 to 51, how does it affect the margin of error? Well, earlier, when we had n equals 34, the margin of error would have been 20.27 minus 17.33 divided by 2, which is equal to 1.47. Whereas in this case, the margin of error when n is 51 would have been 19.98 minus 17.62 divided by 2, and that is equal to 1.18. What we immediately observe is that as the sample size increases from n equals 34 to 51, the margin of error reduces from 1.47 to 1.18. That intuitively makes sense. The more the sample size you get, or the bigger your sample size, the closer you're getting to the population, and more likely, the more information you have to minimize the error. Then for question C, we're to construct a 99% confidence interval for the mean if the sample size is 34. So we want a 99% confidence interval for the mean. This will be equal to, so every other thing changes, but we want to compare this result to what we obtained in part A. In part A, we are going to keep the sample mean, keep the sample standard deviation as 4.2. We're going to keep the sample size as 34. The only thing we want to alter is the size of the confidence interval, or the confidence level of the confidence interval. So from 95%, we want to change it to 99%. Let's go back to StatCrunch. We're going to go to Options, Edit, and we still have all of these pieces. We want to make sure that the sample size is 34 so that it matches part A. And then the confidence level, we want to change that to 0.99 and compute. So in this case, you have 16.83 to 20.77. So we're going to take this result back to our working bench. So when n is 34 and you have all of the same parameters or all of the same information you have in part A, and we only change the level of confidence. The 99% confidence interval for the population mean is 16.83 to 20.77. Why are we doing this? It is because we want to see how increasing the level of confidence affects the size of the margin of error. So in this case, note that the margin of error in this case is 20.77 minus 16.83 divided by 2. This gives us 1.97. So from part A, when the confidence level was 95%, to part C, when the confidence level is now 99%, what we see is that the margin of error has increased. In other words, the more you increase your confidence level, there is a trade-off. You lose precision. So, in other words, the margin of error increases as the confidence level also increases. With that part done, we proceed to the last part of this question. If the sample size is 12, what conditions must be satisfied to compute the confidence interval? What we immediately observe is that our sample size n here is 12. It is lesser than 30. So what we must require is that the sample data comes from a normally distributed population with no outliers. So with that said, we come to the end of that question.